Good morning. Let us now start with the concept of power electronics second session. Uh, Even here also the outcome of this course is to understand the construction and working of the various power semiconductor devices which we have dealt in the last session. Moving on to the contents of today's session that we are going to cover. So control characteristics of the power devices, various power devices followed by some multiple choice questions. So power diodes are made up of silicon PN junctions with two terminals. Anode and a cathode PN junction is formed by allowing diffusion and epitaxial growth. So modern techniques in diffusion and epitaxial process permits the desired device characteristics. The diodes have the following advantage. It has a high mechanical and thermal reliability, high peak inverse voltage, low reverse current, low forward voltage drop, high efficiency, compactness, so on. So if we move on to the next, power transistors are also the devices that have the control turn on turn off characteristics. These devices are used as switching devices and are operated in the saturation region, resulting in the low on state voltage drop. They are turned on when a current signal is given to the base or control terminal. The transistor remains on as long as the control signal is present. The switching speed of the modern transistors is much higher than that of the thyristors, and are used extensively in the DC to DC and DC to AC converters. Remember this. However, their voltages and current ratings are lower than those of the thyristors, and therefore they are used in low to medium power applications. Power transistors are classified as follows: BJTs, MOSFETs, SITs, IGBTs. BJTs, bipolar junction transistors; MOSFET, metal oxide semiconductor field effect transistors; SIT, static induction thyristors; insulated gate bipolar junction transistors. Bipolar junction transistors. Already you have come across many more in-depth concepts on the BJTs with respect to various classifications, modes of operation, so on. Right now, but in a line to speak about with respect to this power electronics, the need for a large blocking voltage in the off state and a high current carrying capability in the on state means that power BJT must have substantially different structure than its small signal equivalent. The modified structure leads to significant difference in the 1 volt characteristics and switching behavior between the power transistors and its low level counterparts. Structure. What is the power? How does the power transistor structure looks? If you recall to the structure of the conventional transistors, we see a thin p layer is sandwiched between the two n layer or vice versa to form a three terminal device with the terminals named as emitter, base, and the collector. The difference in the two structure is obvious. The a power transistor is vertically oriented, four layered of alternating p and n type. The vertical structure is preferred because of its maximize the cross sectional areas and through which the current in the device is flowing. This also minimizes the on-state resistance and thus the power dissipation in the transistor. This is very important. Minimization of the on-state resistance and the power dissipation in the transistor is very interesting point in bringing uh, efficiency, in stating the performance of the stability characteristics of the uh, transistor family devices based on its rating. The doping of the emitter layer and the collector layer is quite large, typically of 10 power 19 centimeters cube. A special layer called the collector drift regions N minus has a doping level of 10 power 14. The thickness of the drift region determines the breakdown voltage of transistor. The base thickness is made as small as possible in order to have the good amplification capabilities. However, if the base thickness is small and the breakdown voltage capability of the transistor is compromised, practically low the power transistors have their emitter and the base interleaved as narrow figures as shown in the figure. The purpose of this arrangement is to reduce the effect of current crowding. So the multiple emitter layer also reduces a parasitic ohmic resistance in the base current path, which reduces the power dissipation in the transistor. Coming to steady characteristics of the coming to steady state characteristics, If you look at the circuit diagram, you'll come to know how the different layers has been divided in order to bring the expectation with respect to the signal level propagation. Coming to the, if you look at the circuit diagram, input and output characteristics, we observe that there are four regions clearly cut off: active, quasi, stay, saturation, and hot saturation. The cutoff region in this area is where base current is almost zero, hence no current flows and the transistor is off. Whereas in the quasi and hot saturation, the base drive is applied and the transistor is said to be on, hence current flows depending upon the load. The power BJT is never operated in the active region, that as in the amplifier, it is always operated between the cutoff and the saturation. The base voltage is the maximum collector to emitter voltage that has been sustained when the BJT is very carrying substantial collector current. The base voltage collector emitter is maximum collector to the emitter breakdown voltage that can be sustained when the base current is zero, and the base voltage collector phase leakage current is the collector phase breakdown voltage when the emitter is in the open state. So means we can find even some of the leakages. This is when the emitter is in the open circuited form. You can also look to the characteristics of a NPN transistor where you find the quasi saturation and hot saturation. Okay, and a secondary breakdown, primary breakdown. So how the transmission is taking part, how the operational responses is taking part in different levels. The primary breakdown shows that takes place because of the avalanche breakdown of the cutter base junction. Large power dissipation normally leads to primary breakdown. The secondary breakdown shown is due to localized thermal runaway. So if you look at the transfer characteristics, which is as shown, which you find with respect to VB and VCC. So VC cutoff, active and saturation, you can find clearly as per the response. You can find the slope response, which is falling from higher region to the region of lower region in an active part. And as we all know, the one most important application of the transistor is a transistor in power electronics is as switching. As it is true that the transistor behaves as a switch, therefore it is used only between the saturation and the cutoff. You can look to the block diagram. This is the common emitter transistor amplifier, which is acting as a switch. The common emitter, common base junction is forward biased with for an voltage of about 0.4 to 0.5 volts. The transistor then goes to saturation. Transistor saturation may be defined as the point above which any increase in the base current does not increase the collector current significantly. In saturation, the collector current remains almost same. The collector emitter voltage increases due to the increased base current resulting in the increased power level. Once the transistor is saturated, the collector emitter voltage is not reduced in relation to the increase in the base current. However, the power increased at a high value of old dry factor. The transistor may be made to be in the active region. VC is increasingly resulting VC increases, which is stating that resulting in the increased power loss. Switching characteristics. If we look to the hybrid equivalent model of the BJT with respect to current gain and the transconductance, the forward bias PN junction exhibits two parallel capacitance, a depletion capacitance and diffusion capacitance. On the other hand, a reverse biased PN junction has only depletion capacitance. Under steady state, the capacitance do not play any role. However, under transient conditions, they influence the turn on and turn off behaviors of the transistors. The internal capacitance, transistor does not turn on instantly as the value of VB rises from the 0 to certain value of V1 say, and the base current to IB1, the cutter current remains does not respond immediately. There is a delay known as a delay time before any cutter current flows. The delay is due to the time required to charge up the base emitter junctions to the forward bias voltage, that is up to 0.7 volts. The collector current rises to the steady state of collector currents, and this time is called the rise time. The base current is normally more than that is required to saturate the transistor. As a result, excess minority carrier charges is stored in the base region. The higher the ODF overdrive factor, the greater is the amount of extra charge stored in the base. The extra charge, which is called the saturation charge, is proportional to the excess base drive. Next comes the turn on time, turn off time, which you are finding with respect to zero point 0.1 to 0.9%, and then from 0.9 it is steady, it's constant based on the applied forward bias voltage. Then it drops as you're finding from 0.9 to again 0.1%. Remember, the fall time is less sensitive to negative bias drive. Fall time is less sensitive to negative base drive. What do you mean by crossover capacitance? You're finding the crossover time is defined as the interval during which the collector voltage VC rises from 10% of its peak off state value, and the collector current falls to 10% of its on state value, resulting as if the function of collector current negative base drive due to the less current due to the collector current negative base drive. If you look to the Thevenin's equivalent thermal equivalent circuit of the transistor for identifying the power derating. So the breakdown voltage. A breakdown voltage is defined as the absolute maximum voltage between two terminals with the third terminal open shared, or the bias in either forward or reverse directions. The maximum voltage is defined as between the collector and the emitter that can be sustained across the transistor when it is carrying substantial collector current. Collector base VCE, collector emitter breakdown voltage, the maximum voltage between the collector and the emitter terminal with base open circuit. Similarly, VCB naught. This is a collector to base breakdown voltage when the emitter is open circuit. So anyhow, we can have a control with respect to the base terminal, hence it is called a base drive control. This is required to optimize the base drive of the transistor. Optimization is required to increase the switching speed. It can be reduced by allowing the base current peaking during that can be increased to a sufficiently large value to maintain the transistor in quasi-state saturation region. The T-off can be reduced by reversing the base current and allowing the base current peaking during a turn off, since increasing IB1 decreases storage time, which you can find clearly in the diagram. Some common type of optimizing base drive of the transistors are turn on control, turn off control, proportional base control, and anti-saturation control. These are some of the measures. Okay, coming to the advantages of BJTs. BJTs have high switching frequencies since their turn on and turn off are low. The turn on losses of BJTs are small. BJTs has control turn on and turn off characteristics since base drive control is possible. BJT does not require combination circuits. These are all some of the advantages of the BJT. We have demerits with respect to this BJT. Drive circuit of BJT is complex. Overdrive factor will occur. It has a problem of charge storage which sets a limiting on switching frequencies. It cannot be used in parallel operation due to the problem of negative temperature coefficient. These are all some of the references as we did for the previous details. Concentrate on some of the interesting multiple choice questions. The advantages of SES over SCR is advantages of silicon control switch over SCR is slow switching time and large voltage, slow switching time and smaller VH, faster switching time and smaller VH, faster switching time and large VH. So here that the advantage of SCS is it has a faster switching time but smaller VH. But whereas in SCR has a faster switching time but it has a large VH. VH should be very small. So within a short threshold holding within a small range of current we can make the device to turn on. But whereas it requires a very large voltage whereas compared to SCR. So which of the following device incorporates a bidirectional switching purpose? Options are BJT. BJT of course it's a bipolar junction transistors. Triac, SCR. SCR is no doubt it's an unidirectional switching device, unilateral, none of the above. But track, here the track is right answer because this device is used for bidirectional switching operations. Thank you.